Okay, we're starting our next session on looking at the electromagnetic spectrum and light. And what we see here is the electromagnetic spectrum. And let's see here if we can focus a little bit more. There we go. And just a reminder that as the frequency increases, the wavelength actually decreases. So when we get a more frequent wave, then it is a shorter wave. We also want to remember that shorter waves have more energy, higher energy here. So things obviously like ultraviolet, X-rays, gamma rays, short waves, high energy. And low energy would be long waves. And then within that we have the electromagnetic spectrum. So we're going to talk about how to do some calculations. And let me zoom out just a little bit here. Oops. Okay. There we go. And we're going to do some calculations. So the first one would be, what if I have a green light? And green lights are generally about 520 nanometers. Okay, so anything in the low 500s, we have green light. So what if I want to know what is the frequency of that light? So a couple of things. So we're going to use the formula that basically says frequency, which is sort of like this cursive V. It's called a nu, the Greek letter. Okay. So frequency is equal to the speed of light divided by the wavelength, which is lambda. Okay? And what we're going to do is then we need to, the speed of light is a constant, so that's straightforward, and we have the wavelength here. Now, when we're solving for frequency, because the speed of light, which is 3.00 times 10 to the 8th meters per second, because the unit is in meters per second, we definitely want to make sure that we have the wavelength in meters. So we need to change the 520 nanometers to meters. So we have a couple of choices. I highly recommend you consider memorizing that anything in the 100s for nanometers is you're going to take two decimal places and you're going to say 5.20. So if it was 630, it would be 6.30, and so forth and so on, times 10 to the negative 7 meters. Okay? Now, if that makes you a little wiggy and you'd like to have a little more hard, cold facts about it, you can simply take 520 nanometers and do dimensional analysis, and 1 times 10 to the 9th nanometers is equal to 1 meter. Nanometers cancel, and when you take 520 and divide it by 1 times 10 to the 9th, you get 5.20 times 10 to the negative 7. Okay, so either of these options would be acceptable. I'm going to take this number now and put it here, 5.20 times 10 to the negative 7 meters. Okay, that allows for me to take meters and cancel them. Okay, and I'm going to take 3 times 10 to the 8th, divide it by 5.2 times 10 to the negative 7. If we do that on our calculator, we get 5.8 rounded to 2 significant. Oh, I have 3 sig figs. Actually, I shouldn't have put this one. That's not significant. So 5.8 times 10 to the 14 inverse seconds, which you can either write as this or you can write as hertz. And that's how we do a problem converting from wavelength into frequency. Now let's do one going in the opposite direction. So we'll work this one a little faster. So say, for example, I have 6.3 times 10 to the 14 hertz. Okay, so I'm going to quickly want to know, well, what's the wavelength for that? Okay, so wavelength is equal to C over nu. Okay, 3.00 times 10 to the 8th meters per second. And my frequency is 6.3 times 10 to the 14 inverse seconds. Okay, Seconds are both in the denominators in both locations, so those can cancel. And now I'm going to take 3 times 10 to the 8th divided by 6.3 times 10 to the 14th, and I get 4.8 times 10 to the negative 7 meters. If I wanted to relate it to the scale on the electromagnetic spectrum, and I'm more comfortable in nanometers, then I can convert this to nanometers. Now remember what I talked about before. If this is 4.8 times 10 to the negative 7, then it's going to be 480 nanometers, which, if you start working on learning your scale, you would say that this is blue in color, maybe a teal. Okay? And that's how you convert between wavelength and frequency.